today as a vice chair for the industry of this technical committee, uh, uh, because Thiago was not able to make it today for some personal reasons. So I will go through the bio sketch of the speaker, a pretty impressive bio sketch here. So I'm just gonna highlight a few part of it. Okay. So Professor Denis Dochain received his degree in electrical engineering in 1982 from the Université catholique du Louvain in Belgium, UC Louvain. He completed his doctoral thesis and thèse d'agrégation de l'enseignement supérieur in 1986 and 1994, respectively, at the same place. And he has been a CNRS associate researcher at LAS in Toulouse, France, in 1989, a professor at the École Polytechnique de Montréal, Canada, in 1987, 88, and 1990, 1992. So he has been with the FNRS. This is a national fund for scientific research in Belgium since 1990. Since September 1999, he's a full professor at the mathematical engineering pole of ICT Institute, UC Louvain, and an honorary research director of the FNRS. Okay, so it's pretty exhaustive. I'm gonna say that he's a full professor at UC Louvain since 2005, and an emeritus full professor since October 2021. Okay, he's a research senior editor of the Transaction on Automatic Control and the Journal of Process Control, an associate editor of Automatica, and former editor in chief of the Journal of Process Control. Okay, in terms of service, it's also quite exhaustive. I'm just going to say that he's a member of the IFAC Council for the coming triennium, 2020-2026. And he has been the co-chair of the International Program Committee of the IFAC World Congress in Toulouse in 2017. He receives the Doctor Honoris Causa title from University of Grenoble in 2019. And his main research interests are in the field of distributed parameter systems, nonlinear systems, parameter and state estimation, adaptive extremum seeking control, with a wide range of application going from environmental engineering to chemical systems and process engineering. He's a co-author of 5 books, more than 175 journal papers, and more than 275 international conference papers. So today, Denis will walk us through his long journey, a 40-year-old long journey, a 40-year-long journey in his research activities in the field of modeling and control of biological systems. So thank you for your availability, Denis, and I will let you take it from here.
Thank you for the introduction, Mamadou. So good morning, good afternoon, good evening, depending where you are. So I would like to, let's say, summarize, all my research activity for more than 40 years. And so really involved in the biological systems for such a long time. So the subtitle is kind of a reference of an old French movie, but it's very difficult to explain, let's say, for those who don't know this movie, what is the connection. Anyway, it's not very important. So let me try to, oops, okay, I have to use key. So if you think of, let's say, biological system is probably the kind of, let's say, image that you have in mind. either something which is very complex in terms of metabolic pathways, and so for those who are familiar with that, it's typically kind of a, let's say, graph that you see in any biologist office, but then you have the Krebs cycle here on the bottom. But it also the complexity comes from what's inside a cell. So a cell is let's say the center of so many different type of let's say items, and it's so complexity is in the middle of, let's say, biological system, if I may say it like that. But in simple words, and it's very simple words, if I want to go back from the start and say what is the simplest way to define a biosystem, well, what is central in any biosystem is the notion of growth. And so we call growth of microorganisms that are sometimes, often called biomass. And so let's say the biomass is to eat stuff, let's say, so it is to consume nutrient or substrate, which are sources of carbon, oxygen, nitrogen, hydrogen, phosphorus, and so on. And this growth can only happen if you have, let's say, favorable environmental conditions, typically, for instance, in terms of temperature and pH. Okay, so if I go back to what I call early challenges, so when I started to work on that, but these challenges are still important today, is that we have to face the fact that we have complexity, and we typically reaction network which is complex. We have to deal with living organisms, so we have to expect that their behavior may change with time. And also we don't know much precisely about, let's say, the way of the matter is transformed, so what we call kinetics. And so because what we have is a mixture of complex biochemical kinetics, and the fact that we have catalytic and autocatalytic reaction, and even the fact that it's multi-phase, so you have typically combination of liquid, gas, solid phases. This is not very helpful to get simple models. So in the end, you can end up with, let's say, complex models, let's say high-order nonlinear models. So this is the first difficulty. The second difficulty is, even today, is still difficult to have access to a lot of, let's say, measurement from the process, either online or offline. So the results of that is it's still difficult to obtain models that are reliable. So this is one of the challenges that we have. So let me try to give you, let's say, an overview of what I would like to talk about. So I would like to concentrate, first of all, about, let's say, modeling. And so try to get soft, let's say, by starting with basic, and then try to generalize it. And then probably what is central for me is the fact that so these models have specific structural properties which are important to consider. And then I would like to move to say a little bit away from that and try to address the fact that we have to know what is inside the cell, metabolic engineering, or the fact that let's say the cell can interact with environments, so this is ecology, microbial ecology, or the fact that also population balances can help you to make, let's say, distinction between, let's say, ages of cells. And then I'll deal also with model identification. So let's start with the simple model. So the simplest way is to say we have a confined medium, which is represented by this tank, let's say, which is supposed to be, let's say, completely mixed. Okay, so in these conditions, let's say if we consider that you have the simplest reaction possible, the fact that you have one substrate used for the growth of one biomass, then we can make mass balance equation for the biomass and for the substrates. Okay, so typically what is inside that is that, let's say, you have a growth term here, and exactly the fact that the substrate is consumed with a coefficient which is known as the yield coefficient, but is related to the growth. Okay, and then this is the quantity of biomass that goes off. This is the term that addition of substrate, and then the quantity of substrate that goes off. So what is nice is it was already this writing with us some kind of generalization, because this model is valid for, let's say, typical operation of, let's say, tanks. So it can be continuous. So you have flow rates Q in and out, and typically it's continuous, they are equal. and the volume is constant. But it can also batch, which is an important, let's say, operation type of operation for this kind of reactor. In that case, there is no inlet flow rate. So we put all the reacting matter in the tank and we let the reaction go on. And so the flow rate is equal to 0. And in fed batch, so you fill partially the tank, and then you fill it until the tank is full. So you have to add an equation for the volume, which is represented here. So what is characteristic of, let's say, biological system with respect to chemical systems is that the growth term, R, is, so this reaction rate is, let's say, proportional to the biomass. What does it mean? It means that if you don't have any microorganism at the beginning, you cannot have growth. So you need to have some microorganisms to start the growth. And then you have kind of a coefficient mu, which is called the specific growth rate. So so this is a key issue, that this assumption is admitted since, let's say, the thesis of Jacques Monod in 1942. And so for convenience, sometimes the people in this field, they say that Q over V is known as the dilution rate. Okay, so mu is not a constant, generally speaking. It is a function, let's say, typically at least on the limiting substrates. And so one typical way to address this issue is to consider what is known as the monomodal, which is an increasing function of S. So let's say the more you heat, the more you grow. But you have also the fact that you can have indigestion. So this is the aldane model. At some point, you see that if the substrate is too large, then you have a decrease in the growth. This model is important, and I will go back to by the end of my presentation to explain a few things about that. But it can also depend on a lot of things. So if you have a product P, for instance, you might have, let's say, some kind of inhibition with respect to P. And what I mentioned before with respect to the temperature is that typically you have to have some kind of condition on temperature to guarantee the growth of some specific microorganism. So this is typically a simple view of that. So mu is a function of the many variables in this case. So, okay, I presented a very simple model, but I can, let's say, consider the fact that we have more complex reactions. And so I take as a first example the anaerobic digestion, which is a wastewater treatment that has, let's say, the advantage of producing methane. It can be a source of energy. It's a very complex process. People in biology, they say it's an open system, so with many different types of microorganisms interacting together. But let's say a simplified way to consider it is to consider that you have at least two reactions. So one is a first reaction when you degrade the organic matter. This is acidogenesis. And so in that case, you synthesize acidogenic bacteria to produce volatile fatty acids, CS2, and CO2. And these volatile fatty acids is degraded in the methanization step by methanogic bacteria into methane and CO2. So that's one way to do it. So if I consider that in a more general context, I can rewrite my simple model in a, let's say, matrix form. And so decide that X is a vector that contains all the concentration of all the components. And then if I do that, what I have are typically two terms. One term which is related to the conversions, when I have R of X, which will be a reaction rate vector, and K, which will be a yield coefficient or stoichiometric coefficient matrix. Okay, and then you have a second type of term, which is the transport dynamics. So F is what you add to the reactor, to the system. Q is what goes off in terms of, let's say, gas. And Q over Vx is, let's say, the dilution term or the quantity of component that leaves the medium. Okay, fine. But then I can have very, let's say, complex model. And so maybe I could use some tools to reduce the model. So I just present one, let's say, possibility to do that via slow, fast, or singular perturbation approach. So the simplest way to explain that, I have a sequence of reaction, A1 giving A2 giving A3. And so I have two reaction rates related to that. What I say is that, okay, A01, K02 is what we are called kinetic constants. And I assume that, let's say, the reaction rate must be, let's say, equal to 0 in absence of the reactant. So if the concentration of A1 is equal to 0, R1 is equal to 0, and the same for the second reaction. Okay, and I have two functions, general nonlinear function F1 and F2 of the components involved in the reaction. So let us define, let's say, the singular perturbation, let's say, coefficient epsilon as being the inverse of the kinetic constant of the reaction. And in that case, we have assumed that the first reaction is slow and the second reaction is fast. So typically, if you, let's say, consider that for a physical point of view, this means that in some terms, any times that A2 is produced, it will be directly consumed to be producing A3. And that's exactly the exercise that we do here. So if I multiply my balance equation of HCA2 by epsilon, I obtain this expression, okay? And so if epsilon tends to 0, what is left is the term here, which is equal to 0. So if I have assumed that phi of 2 has to be non-zero, this means that the concentration of the second reactant, the second component, is equal to 0. In other words, if I make a mass balance of the sum of A2 and A3, so it's what I call C, I obtain exactly this reaction. This means that since Ca2 is equal to 0, this means that I produce A3 from the first reaction. Okay, so this is known in chemical engineering as the quasi-steady state approximation. And I just mentioned that we can generalize it in terms of a general rule for model reduction, which is not important at this point. Okay, so that's the basis. Now let's try to see if we can, let's say, move on to some other, let's say, dimension in the system. Okay, metabolic engineering, population balance, microbial ecology, and I go through each of them now. So in terms of metabolic engineering, so the idea is to try to make the link between the notion of reaction network that I touch a little bit and metabolic engineering to see what's happening inside the cell, okay? And so one of the challenge, let's say, that's metabolic engineering to say, try to address is that can we validate metabolic pathways with a limited number of measured components while preserving the orientation of the reaction. So in this case, we make a strong assumption. We say A give B and not B giving A. So that's, if I may express it like that. So that's the notion of preserving the orientation of the reaction. And so typically, one option is to consider convex basis. I will not elaborate a lot on that, but I can provide you a lot of, let's say, good reference if you're interested by that. But that's one way to keep that. So for those who are not familiar to that, it's not very important to understand that in details at this point. Okay, I'll go back to a simple example. Simple enough, at least, to be able to show that on a few slides, and then I probably discuss briefly one topic, which is one of my favorite topics today, is the link between wine quality and the present production of what we call organoleptic compounds. Okay, so that's my simple example. Okay, as you see. So we have a number of measurements which are in magenta, red, and blue. So typically, we have two types of reactant or substrate, glucose and glutamine. We have 4 products, CO2, at some places, lactates, ammonia, and alanine. And then we are able to have access to 2 types of nucleotides in this case. So this is the information that we have. So, okay, it's already a simplification of a network which is more complex, okay? I will not go into the details into that, but so if I summarize what I said, okay, 2 initial substrate, 4 terminal extracellular products, 2 terminal intracellular metabolites, and on the whole, I have 12 internal metabolites, okay? And if you look at the number of reaction, I have on the whole 18 reaction, okay? It's V8, so 18 reaction, which is complex enough at some point, but simple enough to try to explain what I want to explain today. So metabolic flux analysis is based on my quasi-steady state approximation at the level of the cell, which means that if my general dynamical model, my terms, conversion terms, QR is equal to 0. So as I mentioned, the dimension of the reaction rate is 18. Okay, and in that case, what I had another relation to relate my measurement to the reaction rate. So assume that my measurement can be converted into measurement of reaction rates, and this is what I did. So I have let's say a system of two type of equation, Kr is equal to 0 and Pr is equal to Rm. I use the notion of convex basis to do my metabolic flux analysis. And what I obtained in this case is I obtained 7 microscopic reactions, which are listed here below, okay? So let me try to explain what is behind at least the first one. I mean, because it's probably, I will not have time to go into the details of every macroscopic reaction. So if I look at the previous scheme of what's happening inside the cell, so the flux mode that I call number 1 in this case corresponds exactly to the transformation of glucose into lactate following 2 pathways. So the one going V1, V2, V5, V6, and V1, V2, V4, V6, okay? So that's the one. How can I say that? Because if I look at the first vector of my convex basis, I have 1, 1, 0, 1, 2, 2, and 0. So in other words, I have V1, V2, V4, V5, and V6, and successive transformation of glucose into different terms to obtain 2 lactate at the end, okay? So in other words, I can consider that I have a macroscopic reaction that can be associated to this flux mode, which is exactly glucose giving 2 lactate. So that's the idea of, let's say, metabolic, let's say, flux analysis in this case. Okay, so one of the idea is that we could, let's say, address this issue for more complex, let's say, system. In this case, wine fermentation is typically done via yeast, and so this is typically a very simplified schematic, let's say, view of what's happening inside yeast for the production of ethanol. So this, which is here, so let's say, which will become wine in the present case. So typically, is that how we can transfer in simple model the synthesis of what we call the indicator of the wine quality, which are typically amino acids, but also sulfur compounds in this case. So this is a problem on which we are working for quite a while now, but you know, quite exciting problem. Okay, population balance. We can also have the idea that maybe the age of the cell have an impact on the efficiency of the process, if I may say it like that. So young people are more efficient than old people, if I may say. I may say it like that. And so typically, if you look at yeast, for instance, that I just mentioned before, you have the phenomenon of budding. So let's say the yeast is growing, it's getting bigger and bigger, and at some point it creates a daughter. So, and then at some point the daughter leaves the mother. So that's really the idea of what's happening in the growth of, let's say, yeast. So if I want to consider that, one way to do that is to introduce a new variable, which is the number of cell of mass m at time t per unit volume, which is called the cell density. Okay, so we can have, let's say, the moment of or the 0 in that case, which will be the total number, and the moment of order 1, which will be the total concentration. This is exactly x of t that I mentioned before. Okay, And then I can make a balanced equation for that case. But that's, so what is interesting in that case is that a partial integral differential equation, because what's happening here is that I have this term at the bottom, which is an integral that is clearly related to the let's say the creation of two cells from one cell. So this is, but apart from that, it is, let's say, the transformation into this, let's say, age model of what I did before for the microscopic equation for X. Okay, let's move to the third, let's say, topic that I wanted to mention is, let's say, microbial ecology. So ecology is, let's say, the fact that you consider the interaction of species with their environments, okay? And so typically, what is the basic concept in microbial ecology is known as the competitive exclusion principle. So if I use, let's say, as before, a confined medium, we call chemostats in this case, and I assume that I have two different species, two biomass, X1 and X2, and they have to live on one resource, one substrate, okay? So typically, if I just consider the equation that I used before, extended in this case for X1 and X2, so this is exactly what I have. I have two growth terms for X1 and for X2, and two consumption terms of S for X1 and for X2, okay? So now if I consider, let's say, the equilibrium of that, well, if you look at the first two equations, it's easy to see that this means that mu1 is equal to D and mu2 is equal to D. So that should be the equilibrium, okay? So in steady state or equilibrium, this is exactly one relation that you need to have, okay? But as you can see from my graph, okay, typically this would happen only in this, for this kind of, let's say, configuration at the intersection of the two function mu1 and mu2, which is very specific. So in your general case, and that's the principle in this case, we say that only one species will win the competition and survive, and that's the one which has the best affinity, or what is known as the small break-even concentration, so the one that crosses the first, let's say, the horizontal line related to D in this case. Okay, so in that case, we see that, let's say, in the long term, let's say X1 will survive and X2 will disappear. And it's very easy to show that, and very easy also to extend that to the fact that we have more than two species and other growth curve, as long as they only depend on the resource, on the substrate in this case. Okay, so these are typical, let's say, experimental data. So in this case, is the case when you have this competitive exclusion principle. So in that case, the first, let's say, microorganism is surviving, and the other two, they die. Okay, they disappear. Okay, but what you have also very often is the opposite, is coexistence. Okay, and so this is typically the case where three type of microorganisms, X1, X2, and X3, and they live on one resource, which is glucose in this case, and you see they are very happy to live together. Okay, and then we have also, let's say, something which I can call dynamical persistence. So in this case, is like an open system, like anaerobic digestion, for instance. We have many different species, and so they are characterized here by three colors, just to simplify things. So you have the green one, the blue one, and the red one. And as you see, what's happening, let's say, is from time to time, the blue one is dominating, and then you don't see much green one and no red. And at some point, is the green one is dominating, and then another time is the red one that's dominating. So it's kind of so a way to, let's say, to live together, but then with some kind of domination that changes from time to time. Okay, so this principle is, let's say, kind of contradictory with some of the what is observed in reality. So then I say one solution to have coexistence in terms of modeling is to have indeed models that are they introduce what I call density dependence. So one of the standard model for specific growth rates is known as the contour model. And the contour model is written as follows, but I also can rewrite it as here when I have the ratio of S over X, of the resource over the species, of the substrate of the biomass. So this is this means that I really have what I call the density dependence. So the ratio between the species and the resource in the species. Okay, so in that context, let's say we may say microecology is not limiting to ecology. It can be related to, let's say, practical industrial biosystems. And so it's obvious that knowing better the mechanisms that are behind coexistence or competition of microbial species can be helpful to improve, let's say biological systems. So if I mention invasion of a culture by a contaminant, is typically the case of yeast. So if you produce what is called baker's yeast, or the yeast that you use to produce bread, typically it is still done in discontinuous system, fed batch culture in that case. So in that case, you have to reinoculate the system at every new production. And the reason is because typically what's happening if you run that in continuous culture, at some point you have some kind of other type of yeast that grow, and typically that takes over, but it's not a yeast that has the same property of the baker's yeast. So in that case, well, can we avoid systematic reinoculation by knowing better, let's say, this interaction between these two? And also, two other examples that I would like to mention is mixed culture. So maybe some of you knows that yogurt is a label that requires to have together two types of microorganisms, which are called Lactobacillus bulgaricus and Streptococcus thermophilus. But typically, it's still today they are produced separately. Although we know that there are some synergy when I produce together, but this is not known well enough today to be able to do that at the industrial level. And and the last example that I have in mind is anaerobic digestion, for which we typically people consider there are two types of, let's say, production level, so production temperature. Thermophilic is at 55 degrees centigrade, mesophilic is around 35 degrees centigrade. So that guy, Boris Tatarovsky, has the idea to change the temperature in one reactor from, let's say, from mesophilic to thermophilic and back to mesophilic over some period of time. And he realized that, let's say, the methane production was higher when he does that, when compared as, let's say, two parallel reactor, one only thermophilic and one mesophilic. It's like, you know, I don't know what it means, but that's a fact, and that's probably the fact that maybe, you know, some microbes are resting by while the others are working, and vice versa. Up to you to decide if my interpretation is correct or not. Okay, so let's move now to model identification. So I just mentioned before that this might be a challenge, and I show you a very old results that come from a work from a lady called Adrienne Berg in Finland quite a long time ago. And so what she did, she was trying to exploring, let's say, the reliability of very simple models in that case. So these are typically the data that you have. So this is data in batch reactors. So you have the growth here on the biomass, and here you have the consumption of the substrate. So these are typical data that you have. Not a lot, okay? But, you know, but then if you compare the model and you see, so these are two models with mono, And if you see, typically multiplying the, let's say, the coefficient by 3 doesn't change much. It's impossible to discriminate which one is the best. And so she did an exercise even further. So she decided to initialize differently the optimization routine to get the value of the parameter. And so she did that from 7 to 25, assuming, and which is realistic, that there might be an uncertainty on the initial value of S. And so what you have, you have great, let's say, variability of the parameters up to a point. So in this case, this is the confidence interval, up to a point that's, for instance, this parameter, okay, Ks could equivalently be equal to be negative, in that case, which would be absurd because it's it has some kind of biological interpretation from people in biotechnology. Okay, fine. So that was the first introducing example of the difficulty in terms of identification. But then let me move to a completely different type of biological system. And I hope that you will agree with me that a plant is a biological system. So this is a quite challenging system because plant is a particularly complex biosystem. As you can see, I mean, in plant, you have the roots, you have the stem, you have the leaves, you have the fruits, okay, and so on. And you have also the flowers. So so this is composed of very complex, let's say, different items, okay. And then if you look at, let's say, the growth of a plant is the combination of different items. In the middle, of course, you have certainly photosynthesis and its reverse photorespiration and what's happening during the night, which is called as mitochondrial respiration. So for that, indeed, what you need to CO2, okay? So CO2 is used to absorb, let's say, the carbon which is necessary for the growth. And then it releases oxygen. So this is photosynthesis, photorespiration is the reverse. You need light to do that. But of course, you will need some water, okay? I will not, and we also need, let's say, other, let's say, nutrient, typically nitrogen, for instance. And then I will go back in a few minutes with respect to that. We have also the fact that, let's say, the plant is composed of different items, as I mentioned, roots, shoots, and so on. Okay, and so that's complex. So can we address that? So let me try to explain why I've been working at some point into that. It was the context of a project called MELISA, which is an acronym. Which is indeed, so MELISA is part of, let's say, a project of the European Space Agency to make, let's say, space station autonomous also in terms of food production. So MELISA is a cycle. And so you see at the top, you have the, let's say, the astronauts, the crew. So typically, if I simplify thing, let's say what they do, so humans, they consume oxygen and they release CO2. And what do the plants do? They consume CO2 and they release oxygen. So this is a perfect case when you could, let's say, integrate, let's say, this cycle of oxygen and CO2 into, let's say, a confined medium. And so the idea is that in this case, they will have what they call a chamber, okay, to produce, let's say, the plants. And so the challenge, of course, is to guarantee to have a sufficient production of food by using at best the available resource, of course, in terms of carbon, but also nitrogen. And of course, you have to try to minimize the energy consumption and the water production, the waste production, sorry. Okay, and so that's why I came to my title. So modeling may not be a long, quiet river, especially in this case, because already with biological systems, well, usually the system are slow, but in this case, it's not in terms of, let's say, days that you have to wait, but you have to wait for months before getting, let's say, the full growth of the plants. You have the variability of the growth. I mean, it's obvious that everyone that looks at, the growth of plant, you put different plants together and they won't be exactly the same. So every plant will be different from each other. And also, yes, the diversity of elements that I mentioned before, roots, shoot, leaves, flowers, fruits are different elements from, let's say, different composition. And on top of that, you have the problem of measurements. So how to measure the biomass? So biomass is the mass of the plant. Well, the only reliable way to measure the biomass is to cut the plant, which is not very convenient. So this means that if you do experiments with plant growth, you have to grow a lot of plants, cut a few of them from time to time to get an idea of the evolution of the biomass. Okay, with respect to that, you can say what kind of model shall I choose, simple or complex? Well, you know, my choice is obvious because I always believe the simple models always do a better job than complex models. And so that's what we did. But we did a very, very tough, let's say, assumption. So we only consider photosynthesis, photorespiration, and mitochondrial respiration. And on top of that, we said this is only one reaction. Okay, so we say that the tree can be combined into one reaction as synthesized here, okay? And so that's the idea that we had to try to do that, okay? So typically, if I go back to my screen before, I concentrate of us in red here, in this case. So this is one of the, let's say, experimental results that we have. So we have the biomass on the left. We have carbon dioxide here, so CO2, and oxygen. So what is important to see, so the blue is the measurements. So if you look, you know, in details, you see that, let's say the CO2 is controlled at 1000 ppm during the day, but not controlled during the night, because during the night you have respiration, so release of CO2, and then go back to the day when we control it into the chamber. Okay, so you see that's quite a good fit. We have even better fit than that, but so that's when we consider what I call biomass partitioning in that case. And you see the same for the oxygen. So the evolution of oxygen, compare measurements and prediction is quite good. Okay, let's move to the second part of my presentation, monitoring and what I call software sensors, which is a word which is very convenient for people who are not familiar with state observers. And so in this case, I didn't introduce that notion before, but a key property of reaction system in the general sense is the notion of reaction invariance. So if you consider a state partition of the state X into X and XA such that the submatrix of K index A is full rank, then we know that there exists a transformation Z, which is equal to A0 XA plus XB, where A0 is the solution of this matrix equation, such that we can rewrite the dynamics of the system into a part which is related to XA as before, and a part which is related to Z, which is now completely independent of R, the reaction rate or kinetics, okay? And thus it is an equivalent dynamical model. So it is reaction invariant in the sense that this part is independent of reaction. But it will be a mathematical invariance if you have a closed system. So a system that has no exchange with the environment, because every term here will be equal to 0. Okay, just to insist on the notion invariant here. So how can I use this property in this context of observation, state observation? I consider now that I can, let's say, partition my system into measured and unmeasured variable. Of course, I need some condition of x1, which will be the dimension of x1 will be greater than the rank of the yield coefficient matrix. And so if I write z not in terms of XA and XB, but in terms of X1 and X2, I have this relation, okay? And as long as there exists a left inverse, then I have one way to estimate my unmeasured state X2, because I have to compute Z, okay, by the equation of the previous slides, and then invert the relation here to obtain the estimation of X2. So it's kind of a strange way to say it's an asymptotic observer, but it's just to insist the fact that we can guarantee the convergence. So even we don't have any, let's say, correction term in the observer, we can guarantee that the value, so the observer will converge to the true value. And so the condition is known as, this is a persistence of excitation well known in adaptive control. But this means, in other words, that, let's say, Q over V must not be equal to 0 for too long. Okay, just a second example that I did not mention before, but is PHB. PHB is polybeta hydroxybutyric acid. It's a biodegradable polymer, so a completely different type of biological system as before. Is aerobic culture with this kind of organism, Alcaligenes eutrophus, and it's done in fed batch reactor. So what is important is that we have two limiting substrates: one carbon source, which can be fructose, glucose, it can be methanol, or it can be any type of things, as long as it is a carbon source, and nitrogen source, which is typically ammonia. So what is important is that we have two types of metabolic pathways for the intracellular production. So the PHB is produced inside the cell, okay? One is associated to the growth but with a very low yield, and one is catalyzed via X and an enzyme, which is indeed fully inhibited by the nitrogen. So typically what people do in practice, they first try to produce a lot of catalyst, X, okay? And then when they have enough biomass, then they shift to the second part. So we feed with both substrate in the first step, and then the second step you stop putting nitrogen, and so when nitrogen is consumed, you shift to the second step. So typically these are experimental data for in this case. So this is the volume. So I said it's a fed batch. So this means that the volume will increase until there's some noise. Okay, that's okay. Okay, so that's the volume. This is the constant inlet concentration of. This is carbon source and this is nitrogen. As you see, we stop feeding nitrogen here. And this is the balance of oxygen, so the oxygen in the liquid. This is the inlet gaseous oxygen, is the outlet gaseous oxygen in this case. So this is exactly what I mentioned before. Okay, this is PHB, this is biomass, this is the carbon source, and this is the nitrogen. So I said production of PHB is very low until we don't have any more nitrogen. When you have a high yield of let's say synthesis of PHB, and so typically in this case you have the growth of biomass, and with a slow decrease here due to the fact that the volume is still increasing. So this is the dilution effect in this case, and so this is the carbon, okay, and the nitrogen. Okay, so that's the example that I wanted to show you for this type of thing. So let's move to control. And I would like to first start with, let's say, making the link between control theory and biological regulatory mechanism. So it's obvious that intuitively we can consider that there should be some link between our, let's say, our bodies is behaving in front of a, let's say, a sickness or whatsoever, and so what we know in control theory. So if I look at the dictionary and try to find the definition of what is homeostasis, well, this is exactly what is written there. But then what is interesting is that you find words that we use in control. So it's regulation, the fact that it's very nearly constant. So this is the set point, let's say. And also another definition makes reference to disturbances or preservation of an equilibrium state. So, okay, so that's the first, let's say the first step, but can we make the link with, for instance, PI control? And so what I did is typically drawn from the work of Francis Méret in France. And so I try to give you, let's say, a very simple explanation of that. So we've considered protein X, which has an active state X star and an active one X. So X is the sum of the two. And we have a product, but we has the effect of repressing the production of protein or its activity, okay? And so that's the starting point. I assume that I would like to look for the variation around some reference equilibrium. So with respect to a set point y ref with respect to y. And I assume that the dynamics of the protein is, let's say, the combination of a term of production, a term which is degradation. And I make, you know, f of y, which being, let's say, approximated by a linear relation with respect to this error, okay? And because it is repression, the derivative of f should be negative. So if I write the dynamics of x is what I should have in that case, okay? And so the solution, so I can write the solution, which is exactly this term. So what is great is that I have already an integral term here. Okay, now if I assume that the dynamics of the active the protein can be represented by this relation, okay? So production and consumption in this case. And so if I make a slow fast assumption as mentioned before, so quasi-steady state approximation, I will have exactly this relation between X star, so the active part, and the total protein. And so if I consider the fact that I have no regulation of the activity, so Ki is constant, this is typically what I have. So I have this integral action that comes into the picture, okay? And if I consider that I have regulation of the activity, so here again, I make some let's say, simplification, linearization with respect to E, and considering this relation, and that epsilon is small with respect to 1, then I have obtained a relation for X star, so the active part of the protein, which you have not only the integral term, but let's say the proportional term, okay? And that's exactly what is represented here for the two schemes that I presented before. So that's the standard integral term and the combination of the proportional and integral term in this case, which is typically what we have in a classical feedback representation. Okay, and see, this is an example. So this is the example of the regulation of the ammonia consumption by Escherichia coli by AMTB transporters. So this is one of the examples that I drawn from the work of Francis. Okay, so let's move now to, let's say, control design. And so if I do that, I have to consider two cases. One is stabilization and real-time optimization that I go through very quickly because probably you are fed up by my presentation. I don't want to sleep before the end. So typically what is important to mention, so nonlinear systems mean typically, and this is a very key feature for reaction system, that we may have multiple steady state. Okay, so let's move to adaptive linearization control in this case. A simple example, once again, my very simple example that I use at the very beginning, one substrate giving one biomass. I look at the equilibrium, okay, this is the relation that I mentioned before. I already mentioned that before. So if I look at this equation, there are two options, okay? mu is equal to D or X is equal to 0. X is equal to 0 is clearly not very interesting. In practice, it's known as a washout, because typically in that case, there's no more biomass in the medium. So of course it's not interesting in if you look at the biological system. But if you look at this term, you need to have a model of use. So I used the mono model in my microbial ecology example. But if I take now the aldane model that I mentioned before, the indigestion, let's say, model, if you remember what I said before, in that case, for one value of D, okay, as long as lower than mu max here, one value of D, you can have two value of S. And so it is very easy to show that this equilibrium corresponds to a stable one, and this one corresponds to an unstable one. Okay. So typically, in that case, the objective might be to have to control the unstable modes because this is the most interesting one. Okay, so let me very simplify the approach, what I call adaptive analyzing control, and try to show that it might be an equivalent to PI control in that case. So assume that I have Y is the control variable and Q is the control variable, so the flow in the inlet flow rate, okay? And I make some model reduction, okay? It may be the singular amplitude or the slow fast, let's say, is approach that I mentioned before, some other type of reduction. And so I obtain this kind of relation. So the dynamics of my control variable will be typically, of course, a function of the input, but also typically of some inlet term, which might be from some substrates. You typically, generally speaking, have a term which is related to some gaseous outflow rates and something which is related to the reaction rate vector. Okay. So typically assume that, so very simple dynamics in this case, first order, and I say I want to have a closed loop dynamics which is linear in this case. So the control is very easy to deduce from these two equations. This is exactly this relationship. Of course, I assume that I have uncertainty, and it's a simplified model, but also, as I mentioned, I have a lot of uncertainty in my model, let's say identification and so on. So this uncertainty is transferring to the fact that I shall update alpha, beta, and gamma, and possibly also the reaction rate at the same time. Okay, so that the general approach. I move to my example, anaerobic digestion. Okay, I mentioned so on biological wastewater treatment with production of methane. Typically two-step acidogenesis methanization. So the one that I mentioned is a pilot reactor of 60 liter. And in that case, we were able to have measurement of what you call the chemical oxygen demand, which is a measurement of the pollution in that case, and is assumed to be the sum of the two substrates, so carbon in this case, and volatile fatty acids. Okay, and you also assume that you measure the methane gas flow rates. Okay, and assume that what you want to do is depollution, if you want, so wastewater treatment objective, and regulate the chemical oxygen demand. So if I apply what I did before, the mass balance equation of S can be reduced to that. And this is something that we can do in the general case, okay? And so assume that you want to do some kind of Lyapunov design of my controller. In that case, this means that I will have, let's say, this control inputs combined with an estimation of beta, which will be as follows. So if I look, let's say, put the value of beta adds into my model, this means that I introduced an integrator. So that's what I say. This very simple controller, which is based on my mass balance model, is indeed some kind of PI controller in that case. One a term which is related to the gaseous outflow rate, and here also with the inlet concentration of the substrate. Okay, so this is experimental data. So in that case, we double the load for, let's say, 8 hours, okay, and then go back to the previous one. So this is the control variable, so which was kept close enough to the set points. this is the input variation, and this is the methane gas flow rates variation at the same time. Okay, so let us move to my last example. So I decided, so real-time optimization, that I decided to use a completely different example in that case to show the diversity of biological systems. So I choose a biomedical example in the context of drug delivery, and it's related to, let's say, the cardio-accelerating effect of nicotine, which indeed can be attributed to the buildup of a drug metabolites, but then which is antagonic to the drug, it can reduce the drug effect over time. So typically in that case, this means that you can make a simple model where you have the drug variation and the antagonist variation, which is typically represented by this difference between C and A in that case. And so if you consider that you have some direct effect on the patient, which can be characterized by this relation, so A star is known as the relative potency of the antagonist with respect to the drug, okay? And so if you look at the optimal steady state, it's exactly this value in this case. And a simple objective is to keep E in a prescribed interval, which is called the design interval for the heart rate. So what's happening if the optimal steady state is outside this range? And so that's the idea in this case, is to use an old concept of Sergio Bitanti and co-workers in 1973, which is called the pi test, which says that you can have possible improvement with periodic operation. And so in that case, we can look not at the optimal steady state, but what can be the optimal periodic operation of the system in that case. So periodic drug delivery that maximize the time average of the indicator. So typically this cost function. And so this is typically what we have. We say that there's an improvement in terms of performance in that case. So this is the steady state. This is the optimal periodic behavior in that case. Okay, so, and that's where I say there is here that adaptive extreme seeking control comes into play. So what is important to mention is that we have a biological system. And so this means that the model parameters typically vary from one patient to another. So the periodic optimum, we might know that there is one, but we don't know what it is, okay? And so the idea is that the adaptive extreme seeking controller will be able to find the optimum while controlling the system. Of course, and I mentioned it's a periodic case, but of course it was for static point. Okay, and so just an illustration of this. So I start from this point, okay, and as you will see, I slowly converge to the optimum. Okay, so that's the end of my presentation, and I'll be happy to answer any question that you may have. And maybe I have to stop sharing.
Thank you, Denis. Oh, thank you for this very interesting talk. So many different applications, very interesting. Anyone have questions? Please direct unmute yourself, I guess, then and ask.
Thank you for
I can kick it off, maybe.
Yes, please.
Denis, thank you for preparing this beautiful presentation with so much to learn, so many distinct ideas in modeling and dynamics and control and optimization. I just can't imagine learning more in an hour more than I did in the past hour. I would like to ask you one question that's been bugging me for quite a while, and you have partly answered it towards the end of your talk, but not fully. So in my experience with age-structured chemostats, so population dynamics that have a distribution in age, which you did show one partial integral differential equation model. Maybe that was it. What I was observed is that if you don't model the substrate dynamics, what you typically get is not exponential instability. You may have multiple equilibrium profiles for a given for the right amount of the dilution rate, but you never get exponential instability. In other words, if you're interested in stabilizing open loop unstable systems, and by unstable I don't mean simply growth, I mean having an eigenvalue with a positive real part, you don't find it in such models, and these models are interesting in the absence of a substrate because they are so similar to models that arise in population dynamics in epidemiology. So towards the end of your talk, you showed that if you have a substrate with Haldane dynamics and with indigestion, you get a positive eigenvalue, and there is something to stabilize. But I'm still interested if an open loop exponential instability can arise in models where substrate is not specifically incorporated. And I'm thinking about multi-species models, and you did show one example in which there is, the only possible outcome is the extinction of one and the growth of the other. But anyway, if we do need the substrate dynamics for exponential instability, I will accept that. But if you've seen something where instability can arise without the indigestion being incorporated as the mechanism for this instability, that would be great to know. I mean, the indigestion very much reminds me of the mechanism to instability in machining, in friction driven systems where you have the stick slip instability, and it is because of that negative slope that these things do go exponentially unstable. So sorry about the long question, but it's been bugging me for a long time, for nearly a decade now. How do we get systems that are unstable rather than systems that have eigenvalues at the origin? We just need to move them to the left.
Yeah, I'm not sure that I'm able to answer your question in 2 minutes, let's say. But probably one thing that I would like to stress is the fact that if you consider only the growth of biomass, and you consider there's no limitation in sum of substrate, so typically assume that mu is constant, okay? Then this means that, of course, you will have exponential growth without limits, which is unphysical. I mean, this is not physically possible anyway, because there will be a limits at some point anyway. So the limits are, let's say, conditioned by many factors. And probably one of the factor is the limitation of space. For instance, just that we do not incorporate in that case. Assume that you have an infinite, let's say, resource, and then you don't have the limitation in terms of growth. But then the population cannot grow. It's typically a confined medium that you can consider, and then it can grow any further at some point. So it has to stop, let's say. So, and this is something that we do not incorporate into that. But that's an interesting question. But then intrinsically, growth is exponential, and so that's intrinsic with whatever you do. That's probably the simplest way to address. I mean, to answer your question. But I'm not sure. But the problem is more complex than that. So it's just the way. I mean, it depends on what you put behind, let's say, the model. And all our models have limitations. We know that.
Thank you. Any other questions?
Denis, please, in your age structured representation, you are using the mass as an independent variable, while Miroslav is talking about age. So then there is a mix. Sometimes you use the word age. Are you correlating actually age with mass or?
My fault. It's my fault. I should have mentioned that typically this is impossible to measure the age. Okay, of course, the distribution of age, especially when you have microorganisms, is impossible. So the only way to get, let's say, a good evaluation of the age is the measurement of the mass. That's what the idea that I mentioned, that the yeast is as it's getting old, is getting bigger. Okay, and so you make the assumption that biomass and age are closely related, and it's possible to measure, let's say, evolution of, let's say, mass distribution. So you take a sample, you put that in a measuring system, like it's called call to counter, if I remember correctly, but there may be other, let's say, type of measurement, and then you can get a measurement of the mass distribution. But this is my fault. I should have mentioned that. That's for sure.
Yes.
That's the way. This is the idea of the equivalence between the two.
Thank you. Questions from the audience? So we will thank again our speaker, and we'll be in touch probably for the next seminar in a couple of weeks, hopefully. Thank you so much.
Thank you, Denis. Thank you. Thank you. Bye.